Welcome to This Explainer. Today, we're diving into something truly mind-bending, Stephen Hawking's final theories on the absolute extremes of our universe. Now, if you follow physics, you already know Hawking's life's work was this massive, relentless effort to bridge the gap between Einstein's general relativity on the macro scale and the microscopic determinism of quantum mechanics. But today, we're zeroing in on how he tackled the total breakdown of these laws at the absolute edges of reality. We're going to see exactly what his final works suggest about the very beginning of the universe, its ultimate cosmological destiny, and the incredibly ambitious roadmap this lays out for future scientific research.
There ought to be something very special about the boundary conditions of the universe. And what can be more special than the condition that there is no boundary? Hawking actually threw this profound thought out there way back in 1981 at the Pontifical Academy of Sciences. He was trying to find a way to stop that endless loop of asking, well, what came before the Big Bang? And as you'll see, this decades-long quest culminated in his groundbreaking 2018 posthumous papers. It represents a huge paradigm shift, moving away from static, rigid laws of physics toward these dynamic, emergent structures of space, time, and quantum information.
Okay, here is our roadmap for today. We're going to start with physics at the boundary, move into how he tamed the infinite multiverse, check out the concept of black hole soft hair, discuss this wild idea of a Darwinian cosmos, and finally, look at how we actually test a holographic universe. Let's kick things off with Section 1, Physics at the Boundary. Specifically, we're looking at the semi-classical collapse. So we have to begin at the absolute limits of physical reality, the places where general relativity basically throws its hands up and yields infinite densities and curvature. And this brings us to our first huge cosmological crisis. You see, cosmic inflation does a great job explaining why our observable universe is so incredibly smooth, but it accidentally triggers something called eternal inflation. In this scenario, quantum fluctuations completely overpower the classical evolution of the universe. What you get is this eternally inflating background ocean that just endlessly spits out an infinite fractal multiverse of pocket universes. And here's the massive problem with that. In an infinite multiverse, every physically possible event happens an infinite number of times. That completely destroys our ability to calculate statistical probabilities for our own universe. It makes the whole theory untestable. Physicists call this a severe measure problem. So to put it simply, physics hits a brick wall at two major boundaries. First, you have the initial singularity, the beginning of time, which generates this untestable multiverse we just talked about. Second, you have the event horizon of a black hole. This is where quantum states are supposedly destroyed as the black hole evaporates, creating the famous information loss paradox, which violates unitarity, a core rule of quantum mechanics. Hawking spent his final years trying to mathematically fix both of these monumental boundary crises. Which brings us to Section 2, Taming the Infinite Multiverse, by finding a holographic beginning. To fix this multiverse crisis and actually give cosmology its predictive power back, Hawking teamed up with Thomas Hertog to propose a totally radical restructuring of the early universe. They realized semi-classical gravity just doesn't work during eternal inflation, so they pulled in the holographic principle. Instead of trying to do the math for a chaotic, eternally inflating 3D space, which is a nightmare, they just excised it completely. They mathematically replaced it with a 2D spatial boundary surface, essentially a conformal field theory that acts as the exit plane of eternal inflation. The best way to visualize this is to think of the universe like a shuttlecock. At the wide top, you have the expanding cosmos we experience today, complete with the dimension of time moving forward. But if you trace it all the way down to the tiny point at the bottom boundary, time is entirely projected out. It literally loses its fundamental meaning, leaving nothing but pure space. In this view, time isn't a pre-existing clock ticking away in the background. It's an emergent property that sort of crystallizes as the universe exits this timeless holographic phase. And the results of this are amazing. By applying really strict mathematical and geometric constraints, Hawking and Hertog evaluated the probabilities of different boundary conditions. They discovered that a highly irregular, fractal-like boundary has an exponentially tiny probability of existing. Through this really elegant math, that messy, infinite fractal multiverse is tamed. Instead, the Hawking-Hertog model predicts a globally finite, reasonably smooth cosmos. And just like that, predictive power and scientific testability are restored to quantum cosmology. All right, let's jump into Section 3, Black Hole Soft Hair, and how they went about rescuing quantum mechanics. So, having tackled the beginning of time, Hawking turned his attention to the event horizon. Now, classical physics has this no-hair theorem. It says black holes are basically featureless spheres defined only by mass, spin, and charge, meaning any quantum information that falls in is lost forever. But Hawking, working alongside Andrew Strominger, Malcolm Perry, and Sasha Hagrako, pushed back on this. They proved that null boundaries, like an event horizon, actually possess an infinite degeneracy of vacuum states. They called these zero-energy excitations of photons and gravitons soft hair. Here is how it works in practice. Imagine a massive object falling into a black hole. As it crosses the horizon, it excites these soft modes. Now, because they carry zero energy, they don't alter the black hole's classical mass or spin. But, and this is the genius part, they do leave a holographic memory, a microscopic quantum imprint, right on the horizon. So for someone watching from the outside, this mechanism theoretically preserves quantum unitarity. It stops information from being permanently erased from existence. This is a massive deal because it theoretically saves the entire foundation of quantum mechanics. And the mathematical proof they came up with is just stunning. Using string theory principles, the team calculated the microscopic charge of this holographic field. The result? Exactly 12 times the black hole's spin, or 12J. When you plug 12J into standard equations, this purely quantum calculation perfectly matches the already known macroscopic thermodynamics of black holes. It provides concrete, microphysical evidence that the information is actually preserved.
Moving on to Section 4, a Darwinian cosmos, and the evolution of physical laws. So Hawking synthesized all these boundary solutions into a really profound philosophy, which Thomas Hertog detailed in his work On the Origin of Time. Hawking championed what he called top-down cosmology. The idea is, because we exist inside the universe, we can't take some external God's eye view of a pre-existing multiverse. We have to reason backward from what we observe today. And that suggests physical laws are not these immutable, eternal truths that just floated around before the Big Bang. Instead, they co-evolved and crystallized as the universe expanded. It's almost like a Darwinian natural selection of physics. This implies that our universe's cosmological destiny isn't determined by a random infinite multiverse, but by emergent laws that forge themselves specifically to allow our existence and then slowly fade away as you trace them back to that timeless holographic boundary.
When you look at this table, you can see how beautifully this entire paradigm comes together. Whether he was confronting the beginning of time or the edge of a black hole, Hawking consistently mapped 3D bulk physics onto a 2D boundary surface. In both of these seemingly different cases, he used conformal symmetry algebras to solve intractable paradoxes. He literally linked the multiverse measure problem with the information loss paradox through the mathematics of holography. It's just a brilliantly unified way of looking at the cosmos.
Now, we're explorers of science here, so we have to be totally objective. These ideas are groundbreaking, for sure, but they face some really healthy, rigorous skepticism from peers. For instance, Neil Torok critiques the underlying math, arguing that stabilizing the universe's wave function requires complex integration that actually violates physical causality. Then you have Andre Linde, who points out that the equations still permit multiple inflating domains, meaning the multiverse might persist anyway. And let's not forget the hair loss paradox. As a black hole eventually evaporates and shrinks, how is the information stored in that soft hair actually transferred into the outgoing Hawking radiation? These are still massive hurdles for theoretical physicists to clear.
Which brings us to our final part, Section 5, testing of the holographic universe. Let's look at the future frontiers. Because, a beautiful mathematical framework is really only half the battle. How do we actually go out and test this? Well, the roadmap relies heavily on our next-generation observatories. That transition out of a timeless, holographic state is predicted to generate long-wavelength primordial gravitational waves. The upcoming space-based LISA observatory is perfectly designed to hunt for those, alongside specific polarization patterns in the cosmic microwave background. On the black hole side, the Event Horizon Telescope could potentially measure these tiny, fractional shifts in a black hole's shadow caused by that soft hair. Plus, future gravitational wave detectors might catch high-frequency ring-down modes when black holes merge. So yes, the pursuit is incredibly challenging, but these observational signatures are theoretically within our grasp. Stephen Hawking's final legacy leaves us with a deeply unified and, most importantly, a testable vision of a self-contained universe. By taming the wild infinities of both the multiverse and the black hole, he challenged literally everything we thought we knew about the cosmos. And so, we're going to end this explainer on a rather profound question for you to ponder.
Are the physical forces and immutable laws that govern our everyday lives not eternal truths at all, but merely a holographic projection crystallizing from the timeless dawn of creation?